I have to work on a study guide about logarithms.
Okay.
So the first question is evaluate the logarithms. And it's log 4 and then 16.
Okay. What I've always found helpful in doing these is adding a variable.
Okay.
Make that equal to x.
Okay.
Because it is a number. We just don't know what number it is yet. Okay?
Okay.
Now once you've added the variable, translate that to exponential format. What is the exponential format of that logarithmic expression?
It's y equals, right?
Now hold on, there's no y in there. There's
Oh.
only three things. There's a 4, there's a 16, and there's an x.
Oh, okay.
Put them together.
So, do you subtract?
Here's what I do. I'll tell you the way I memorize it.
Okay.
The number on the far left raised to the power on the far right equals the number in the middle.
Okay.
So it's 4 to the x equals 16.
It's not x to the 4?
No. Here's the thing you have to remember. Logarithms are exponents.
Okay.
That's the only thing you have to remember, really. Well, it's not the only, but it's the most important. If you always remember that logarithms are exponents, then this x, which is on the other side of the equation of log, has to be an exponent.
Okay.
Okay? But the fact is that this method, I think, works rather well. Number on the far left raised to the power on the far right equals 16. Always remember that logarithms are associated with exponential type equations.
Okay.
This is not an exponential equation. This is an exponential equation. What's the difference?
It's to the power of x?
The variable is in the exponent. If the variable is in the exponent, it's an exponential equation.
Okay.
If the variable is not, then it's not. It's an algebraic equation. And the difference is dramatic. You cannot solve exponential equations with algebra. You have to use logs. Now, in this situation, they're giving you a log equation, which we convert to exponential because why? What's x?
X equals 4.
4 to what power equals 16?
Oh, 4 to the 2nd.
That's what x is. In other words, because we were able to convert it to an exponential equation that was an easy one, we were able to do it. Now, let's change it for a moment so that that number is 15.
Well, I have a harder one.
Okay, go ahead.
Log to the 6 and then 216 to the x power.
Like that?
Yep.
Okay. Let's make that equal to y. Since I can't make it equal to x because that variable is already in use.
Right.
Now, one of the properties of logs is that if the argument is being raised to an exponent, then you can rewrite it by putting the exponent in front of the log.
Okay.
So I can rewrite that as this. in fact, let's take away this variable because at the moment it just makes it confusing. Okay. Now, what is that equal to? 6 to some power equals 216.
Okay.
What is that? What
So, are you asking me what to...
6 to what power equals 216? And let me give you a clue. The answers are always small whole numbers. They're never 2.4. They're never 18. They're small whole numbers. They're either 1, 2, 3, or 4. Well, what is it? 6 to what power
4.
equals 216?
6 to the 4th power?
Well, let's do that multiplication.
Or 6 to the 3rd power?
Ah, that's 36 times 6, which is equal to 216.
Okay.
So this I can basically cross off and replace it with a 3. So the answer is 3x for this expression. In other words, okay, what else, Anna?
Can you help me with graphing them?
Yes, absolutely.
Okay. One is, it asks for the parent function first, and then y equals log 3 parentheses x minus 1 parentheses.
Okay. What do you think the parent function is?
Y equals log 3?
Of x. Got to be 2 variables in there.
All right.
Y and x. Okay. Now, if I graph the parent function, it looks like that. But the fact of the matter is, and it goes through that point 1, 0. The fact is that all log functions look like this. That could be log base 13 of x. And it would look exactly the same. All log functions go through this point 1, 0. You with me?
Yeah.
Okay. Now, what's different about that? What kind of a transformation is that?
Shift right 1?
Okay. That means the one point that I know about gets moved to there, which is 2, 0. And not only does that point get moved, but we had a vertical asymptote on the original parent function. What was the vertical asymptote on the parent function?
0?
X equals 0, yes.
Okay.
What's the vertical asymptote on this function?
Y, or x equals 2?
1. Remember, it was only
moved
1.
Okay.
It was moved 1 to the right, and that moves the vertical asymptote 1 also. So the red function is this function here, and the red dotted line is the vertical asymptote of that function.
Okay. Let's see what else. Okay, for these, I'm allowed to use a calculator.
Okay.
But it says solve each equation, show all work.
Okay.
But it's 3 to the x equals 1 over 27.
Now, even though they told you you could use a calculator, you don't really need to here.
Yeah.
Here's the thing. This is an exponential equation. 99% of the time, you have to use logarithms to solve an exponential equation. This is one of the few times that you do not have to use logarithms.
Okay.
And the reason is that there is a common exponential base between those two numbers. And it is 3. In other words, I can express this as 3 to the 1 raised to the x power. How can I express 1 over 27 as 3 to some power?
I'm not sure.
It's 3 to the minus 3.
Oh, okay.
In other words, remember what negative exponents mean. They mean 1 over 3 cubed. That's what they mean. Remember that. Do not forget it. I cannot tell you how much trouble I have getting my students to remember what negative exponents mean.
Okay.
For some reason, it's like Chinese arithmetic to 90% of my students. No matter what I say, they do not remember what negative exponents mean. Well, this is what they mean. They just mean reciprocal. That's it. In other words, 2 to the minus 4 is 1 over 2 to the positive 4. That's what they mean.
All right.
Okay? So, that's why I can write 1 over 27 as 3 to the minus 3. And I don't need that 1, so I really have 3 to the x equals 3 to the minus 3. What do you think x is equal to?
9?
If my bases are the same, and I got one base to one exponent equals the same base to a different exponent,
Oh, then it's just 3, right?
minus 3. In other words, the exponents have to be equal. You cannot have, if I have b to the x equals the same base to the y, then the only possible thing is b has, or x has to be equal to y. So when you get the same base equals different exponents, the next step is to equate the exponent. And when you do that, you solve it instantly. In other words, x is equal to minus 3. Because that is equal to that.
Okay.
Okay, what else?
There's, condense and solve the equation, check for extraneous solutions.
Okay.
And it's log 3 14 plus log 3x equals log 3 42.
Hold on a second, I wrote that wrong. You said log 3x equals what?
Log 3 42.
All right, there's 3 very important rules of logs. The log of a times b is equal to what? These are three rules that you got to memorize or you're going to flunk logs. That's bottom line. Seriously. You got to memorize these 3 rules. So that's the log of a plus the log of b.
Okay.
Second rule. The log of a divided by b. When that's in the argument, that's equal to the log of a minus the the log of b. And finally, and this might be the most important one of all, the log of a to the b power is equal to b times the log of a.
Okay.
So look at those three rules, make sure you understand them.
Yeah, I wrote them
Able
down.
to go both ways. They're going to ask you as many problems that go that way as go that way. In other words, they're going to say expand this or condense it. If they say expand it, they're going to give you something like that.
Okay.
If they say condense it, then they're going to give you something like that. Well, in this case, they give you two separate log expressions, right?
Right.
That's a condensed problem. So what is it condensed to? In other words, can I turn that into a single log expression on the left side of the equation?
Are you asking me or?
Huh? Absolutely. I'm always asking. You know that, Anna.
Oh yeah.
I tutor. So
You.
this expression turns into what based on my three rules?
So that'll turn into. Well, don't I put the 3 in front of the log?
Well, first of all, these three rules are dependent on the base being the same everywhere.
Okay.
In other words, if this was log base 3 and this was log base 4, I could not apply any of these three rules. So the number one requirement is that the base be the same everywhere. And that's all you're going to get. They're not going to give you problems with different bases. They don't do that.
All right.
I've been tutoring for 8 years. I've never ever seen a problem that said log base 4 of 14 plus log base 5 of x.
Okay.
They just don't do it. They give you the same base. And
So
as long as it's the same base, then you can apply these three rules, whichever one fits.
Okay, so will it end up being log 3, and then parentheses 14x?
Yes. Perfect.
Okay.
Okay. Now, I'm going to erase those three rules, although, boy, if you wanted to take a snapshot of any screen, this would be the screen to take it of.
Yes.
So you might want to consider doing that.
Okay, just a second.
Okay?
Okay.
Those three rules, those are the most important three rules of logs. Now, let's go from there. I got to erase it because I need writing room. Now notice that I have the log base 3 of 14x equals the log base 3 of 42. Well, what can you say from that information?
Well, can't I? I don't know what I can say.
You can equate the arguments. That's the argument. That's the argument. Since it's log base 3 in both situations, then I'm going to make 14x equal to 42. That has to be a true statement.
Okay.
And that makes x equal to 3. All right, what else you got?
Okay. And then, oh, it asked me to check my solution.
Well, I did. I didn't talk about it, but I did actually check your solution. And by checking it, I plugged it 3 in for x.
Okay.
And the only thing you really have to check for is to make sure that you do not violate the domain. Now, if I had an answer of -1, then that means that violates the domain. The arguments always have to be greater than 0.
Okay.
You cannot take the log of a negative number. You can also not take the log of 0.
All right.
So it's more restrictive than the square root function. If I had the square root of x, x merely has to be greater than or equal to 0. But if I got the log of x, x has to be greater than 0. Might seem like a subtle distinction, but it's not. Logs have to be positive. You cannot take the log of 0. You cannot take the log of a negative number. Now, frequently, when you have log equations, you'll end up with 2 solutions. In this case, we only ended up with 1. And it did not violate any of the domains. But a lot of the times you'll end up with 2 solutions. You end up with a quadratic, you have to solve it, you'll get 2 solutions, one's positive, one's negative.
Okay.
Plug both in to the original function, and I mean the original, not this one, the second line, but the first line. And if one of the solutions violates the domain, it's out. Cross it out. It's not one of the solutions. And the other solution should work, and it will not violate the domain. Now, in terms of checking this, that's what she meant. She meant, does it violate the domain? She didn't really say that. She says, check your solutions. So let's check our solution. Is this a true statement, what I'm writing here? That's really what checking the solution means.
Okay.
Does it work? Does it satisfy the equation? Well, not that easy to do, but what's that equal to?
Log.
How much?
Well, it's equal to, I'm trying to think.
Well, let's go through that, because this is like one of the most important things about logs. You've got to know this. If I'm trying to evaluate that, I'm going to set it equal to x, just because it makes it easier to understand. Now convert it to exponential format. That's the...
Oh.
Convert that to exponential format. What is it?
So that'll be 3 to the x equals 3.
What's x?
X equals 1, right?
Huh? So
okay.
The log base 3 of 3 is 1. And in fact, the log base 17 of 17 is 1. The natural log of e is 1, because that's really log base e of e. So the general formula is the log base b of b is always equal to 1, by definition. Now, the fact that we know that's 1 doesn't help a whole lot. You still can't really check your solution, because now we have the log base 3 of 14, which is an irrational number, plus 1 equals the log base 3 of 42. And I have no doubts that that's a true statement. But proving it is more difficult. In other words, you could go into your calculator and get a number for that. Even that's tough. What kind of calculator do you have, Anna?
I have Inspire Cast, I think.
Okay, yeah, I'm familiar. I got one of those. But even this is tough because most calculators deal with natural logs and common logs. When you have a log to a base that's other than 10 or e, you have to use the change of base formula. So this expression becomes log of 14 divided by log of 3 plus 1. Is that equal to the log of 42 divided by the log of 3? Well, guess what? It is. Even though I can't prove it to you, if you do that in your calculator, you'll see that it is equal.
All right.
Okay. Yeah, no, we covered a lot of important log principles here. And
yeah.
I mean important.
Yeah.
If you want to have any chance of understanding logs, you got to understand everything that I said today. And if you don't, I would recommend you reviewing the recording of this.
Okay.
So that you remember the rules of logs. Because you can't really do anything if you don't remember some basic rules of logs.
Okay.
All right?
All right.
Anna, now, hold on. Before I let you go, let's talk about the schedule.
Okay.
Because we've had some problems here.
Yeah.
I don't want to keep giving you this 8 o'clock spot on Tuesday if you're not going to need it.
Okay. Yeah.
I'm going to be booked solid for the next 3 weeks. So,
well, I'll definitely have it Tuesday next week.
Okay. That's good enough. We'll leave it there.
Okay.
And we'll talk again, and you can tell me whether you're definitely going to need it the week after that. Because if you're not going to need it, I want to allow somebody else to use it. So.
Okay. Yeah. No, I'll need it.
Okay. Cool. So I will talk to you on Tuesday, May 9th at 8 p.m.
All right. Sounds good.
Okay, Anna. Bye-bye.
All right. Thank you.
Good week. Bye-bye.